Okay, welcome to this lab on inventory optimization in Python. So this lab is really simple from a Python perspective. You just have to call some functions and they give you the optimal inventory parameters. But it's important to learn about this package and what are the arguments you need to pass to the function. And so I will cover all of that. If you're familiar with inventory models, you'll find this easy. Now, all the inventory models we cover today are covered in supply chain courses. So, if you have taken the prerequisite courses, you would have seen all of these at some point, although you may not remember all of them. But the good thing is, if you understand this code, what it's doing, you can do all these calculations without having to go back to manual formulas and so on. So we're going to use this package called Stockpile, which has a lot of functions built in to do inventory calculations. This is a link to the documentation, so I recommend you open this, accept the redirect, and then it has these modules: EOQ module, news vendor module, SSRQ, all these modules. And when you go to a module, it tells you all the functions in it, what are the parameters, what is the output, and so on. Okay, so to begin with, you have to install the package. So we do !pip install stockpile in Google Colab, and this will install the package. And I like to hide the output. Then you need to import the package, and then we can start. So the first thing we're going to do is the basic economic order quantity calculation. So if you recall, this calculation tries to find the optimal costs by looking at ordering cost and cycle inventories holding cost. So the bigger orders you place, let's say you order large amount of quantities of material, you will have high inventory, then your inventory holding costs will go up. But if you place small orders, you'll have to order more frequently, and each time you order, there's an ordering cost because you might have a transportation expense that's like fixed. You might have a financing cost or some documentation cost. You may have employees associated with handling the processing of an order, like placing the order with the supplier, getting the invoice, paying the invoice. All of that employee time involves labor cost that can be part of the ordering cost, right? So how do we calculate EOQ? So let's look at this example. Joe's Corner Store sells 1,300 candy bars per year. Costs $8 to place an order to the candy bar supplier. Candy bar costs the store 0.75. So each candy bar that you buy, you pay the supplier 75 cents. Holding costs are 30% on the value of the item. So what is the optimal order quantity? Now, notice that we have to do something here. First, from stockpile, we have to import the right function. So the function we need is economic order quantity, and you have to import it from the right module. So you have to do from stockpile.eoq, import this. How do I know all of this? If you go to the documentation and you look at the EOQ module, and this is the function that you need. So now you know, okay, this function is in the EOQ module in stockpile. So I'm going to do from stockpile, which is the package.modulename.eoq, import the function you need. Now this function expects a holding cost, which is not a percentage. You can't pass it 30%. So holding cost has to be in dollars. You have to multiply the 30% with the value of the item, which is $0.75. This will convert the holding cost in dollars per unit per time period, and then you can pass on that holding cost. Notice that in Python, we can have named parameters. So when you call a function, you can say this parameter of the function equals what value you want to pass it. So here are the parameters to economic order quantity in the documentation. It takes in a fixed cost, a holding cost, a demand rate, and order quantity, which is optional because it's supposed to calculate the order quantity. But if you already have an order quantity and you want to just get the cost of using that order quantity, you can pass that in. But these are the main arguments which don't have the keyword optional, right? And so I know I have to specify these three arguments. Now the first one is fixed cost, the second one is holding cost, the third one is demand rate. So I could just say like this, 1,300, demand rate is the third one. So how can I pass demand rate first? That's the beauty of named arguments. I don't have to remember this order that I have to pass fixed cost first, holding cost second. As long as I do something like this, demand rate, which comes from here, equals, and whatever I want to pass it. Fixed cost equals 8. Holding cost equals the holding cost variable I defined right here. So whatever comes after equal has to be a value, like a number, or has to be the name of a variable you define in your code. And whatever comes before the equal sign right here has to be the name of the parameter which is given in the documentation. So when you use these named parameters, when you're specifically telling the function, okay, demand rate equals this thing, then the order does not matter. You could write them in any order. You could put demand rate first, you could put demand rate second, you could put demand rate third. It doesn't matter because you're giving it the function, you're telling Python the name of the parameter that you're assigning. But if you don't pass in the name, you could do something like this, economic order quantity. And now you have to pass in the fixed cost, which is 8, then the holding cost, which is holding cost, and then the demand, which is 13. So they have to be in this order. Fixed cost, holding cost, demand rate. Why? Because I'm not specifying the name of the parameters. I'm not telling Python this 8 it goes to which parameter. So Python is going to go by position. Okay, 8 is the first thing you're passing me, and this code expects fixed cost to be the first thing you pass me. Okay, so 8 is going to go to fixed cost. Right? But you can take out this order-based passing by just specifying the name of the parameter, which is what I like. Because look at this. This code is a lot more readable. I know exactly what my fixed cost is. It's 8. My demand is 13. But here, I don't know what the 8 is. What is this 8? Right? You have to think and you have to go check the documentation. Oh, 8 is the fixed cost, right? So it's much harder to read this type of code. So just code like this by specifying the names of the parameters equal and then whatever value you want to pass it. Then we want to print out the value. So we print optimal order quantity is Q, and then the annual cost is cost. So if you look at this this function here, it returns two things, order quantity and cost. So you can accept multiple return values by splitting them with a comma. Okay. So let's run this. Okay, we did. Yeah. So Q is your economic order quantity, which was 304. And then the annual cost of using this Q is 68, which is the minimal cost, just minimize the cost. Now, what if the store said, well, you know, I don't want to order 304 because 250 candies fit in a nice box, which can be shipped to me or whatever reason. So what if I was to use 250 order quantity instead of, you know, the optimal 304? So we can call this function again with the exact same arguments, but this time we can specify the order quantity. Here, I don't optimize the order quantity. Use this order quantity of 250 that I'm specifying in your parameters. And then it'll just give you the 250 back as Q, and it'll calculate the annual cost for using 250. And you can see the annual cost is slightly higher because using a suboptimal order quantity. Now, this is a very nice extension. Sometimes companies want to order multiple products from the same supplier. So in addition to there being a fixed ordering cost, there is also going to be an ordering cost per product, or an individual ordering cost for each product you order from the supplier. So if a supplier sells you 5 items and you order only 1, it's going to be cheaper than to order 5 because, you know, you have invoice is going to be more complex. You're going to have 5 line items there in the system. Entry is going to be more complex. Maybe your shipping company is going to charge you more because they have to pick up different types of products and, you know, make sure they go to you. And so all of these cost differences can sometimes result in, okay, I'm ordering 5 or 10 items from the same supplier. There's a fixed cost for each order I place, but within the order, if I order, you know, 5 or 10 items instead of 1 item, each line item adds a little bit to my ordering cost. So that's our setup. So the same setup applies if you have multiple suppliers close by, like in the same city or town. Shipping companies can pick up your orders from multiple suppliers in a milk run on the same day when all the orders are ready, but they'll charge you for each stop because it costs them more to add stops to the pickup route, right? And so this is the setup we're doing. So Joe's Corner Store orders 2,400 Chewy candies 1,800 lollipops, 2,950 sour gummies each year from nearby suppliers. Fixed ordering cost is $25, but there's an individual ordering cost for each candy, which is $20. Okay. So if you were to place the order for just chewy candies, you would have a $25 ordering cost and a $20 cost for the chewy candies. But if you place an order for chewy candies and lollipops, then you would have $25 worth of ordering cost, an additional $20 for chewy candies, and an additional $20 for lollipops, for a total of $65 cost for that order. Holding cost for each item is given. What are the optimal order quantities? So here we have to have a shared ordering cost parameter, which we set to 25. First, we import the right function. So from stockpile.aoq, we import joint replenishment problem silver heuristic. How do I know this is the complicated name of the function I need? I go to the API reference, I scroll around, okay, then here it is. The joint replenishment problem, which is this type of a problem. This is the function to solve that. Okay, so I look at the parameters. I need a shared fixed cost, so I'm going to pass it in the $25. Individual ordering cost needs to be a list of, and the list has to be as long as the items you have. We have 3 items, so we need 3 pieces in our list. So you can just specify it like this, in square brackets, 20, 20, 20. That's your individual ordering cost for each product. And a shorthand for writing this is 20 in square brackets times 3. That means repeat 23 times. Holding costs for each items are different, so I can't do 0.3 times 3. I have to do 0.35, 0.3, and 0.45. And demand rates are also different, how much we need for the year. And then we just call this function, so it returns order quantities, a base cycle time, and order multipliers and cost. It returns 4 things. So if you go to the documentation, it returns these 4 things. So you assign them to 4 variables, variable 1, comma variable 2, comma variable 3, comma variable 4, equals your function call, and you pass it in all the parameters. And then you can print all of this information out. So your optimal order quantities are, you want to order 601 or 602 chew candies at a time, 451 lollipops, 739 sour gummies. You're going to order every 3 months. Okay, that's the base cycle time. And order multipliers are 111, which means each product is ordered every month. If a product doesn't have a lot of demand, it will sometimes get an order multiplier of 2, which means skip it every other order. So if you order this item, this order, skip the next order, then the next one you can order it. So let me reduce the demand of something like this to like 100 to show you. And then you can see, because lollipops, I said, its demand is very low, you are going to order, your base cycle time is still about 3 months. You're going to place an order every 3 months. But every time, with a multiplier of 1 means every 3 months, you're going to order your chewy candies with demand of 2,400 in the year. But only every fourth time, you're going to order the lollipops. So you basically order like about 100 once and you're done, because every 4th time, when you're ordering every 3 months, is a whole year. 2.97 times 4 is almost a year, right? So every 4th ordering cycle, you're going to order the lollipops because you need so few of them, and then every ordering cycle you'll order the sour gummies. Actually, let me make this like 800. So this is every 2. So now you order 380 of the lollipops, and every 2nd ordering cycle, every ordering cycle comes every 3 months. So the base cycle time is after how many months do you order, and the order multiplier tells you whether you have to order that product on every ordering cycle or not. So this is very nice in handling multiple products being ordered together, either from the same supplier or close by suppliers, where you can combine them in the shipment. Okay, now this is a very, very key calculation. Okay, oftentimes, okay, so this, some mistake happened. Let me take it out. Okay, so This is very common. So often you have seasonality in your sales, and so your demand is not constant throughout the year. If you have the same ordering quantity and you keep the same ordering quantity for the whole year, when you have a peak selling season, that ordering quantity may not be enough, right? So EOQ, all of what we did till now assumes like a constant demand throughout the year. But oftentimes demand is not constant, it goes up and down. So if that is the case, you can just have a forecast of the demand. So if we have a children's toy car and to the next 12 months, we have the monthly demand. So you can see the year starts off with 800 demand, not very high. Then the demand kind of peaks in June. So the first month is January, February, March, April, May, June. June, the demand goes up to 1800, but the demand really takes off in December on the Christmas season. Okay, so you have the other parameters, holding cost, ordering cost is given. So you can just pass demand as a list, with 12 values for the 12 months to the Wagner-Witten algorithm, Wagner-Witten algorithm, and you import it by saying from stockpile.Wagner-Witten, import Wagner-Witten, okay? The holding cost is going to be interesting because this algorithm wants you to give it a holding cost per time period. Remember, we have 12 time periods, we have 12 months. And usually our problems specify the holding cost per year. It costs $8 to keep one toy car in inventory for 1 year, right? So you have to divide your annual holding cost by the number of time periods in the year, because we have monthly demand, the number of time periods are 12. If you had weekly demand, you would have 52 time periods in the year, and then pass it in the holding cost per time period. Then you just call Wagner-Witten, and then you pass it the number of periods, which is the length of this list, which is 12 periods because we have 12 values. Holding cost is the holding cost that we specified here. Ordering cost is that. We pass in the demand values, and it tells you the order quantities and the total cost. You can ignore the last two things it returns, cost to go and next order periods, because basically you just need these two to make your decisions. And so, but you still have to specify a comma, specify these, because it's going to return 4 values. If you go to the Wagner-Witten module, this function in there, it returns 4 values. So you have to have 4 variables. You can just call this like, X and Y if you want, right? Doesn't matter. And then you can ignore them, but you have to have 4 variables, variable 1, comma, variable 2, comma, variable 3, comma, variable 4, equals, and then you call this function, and then you can print out the ordering quantities and the total cost. So you can see that, and Wagner-Witten will always place an order in the first time period because it assumes you start with 0 inventory. So you don't want to wait sitting on 0 inventory. So you always have to place the order in the first time period. So you place an order of 1600 for the first time period, which will last you 2 months, right? So then you place an order of 0, like no order in the second month. Then you place an order of 1900 after that, okay, which is going to be okay for the next 2 months. Then you place an order just for 1 month. Then you place an order for 2 months, and so on, right? So because it's trying to, because you have an ordering cost, it's trying to not, it's trying to balance all the costs to give you minimum total cost. There's an ordering cost, there's a holding cost. If you order too much at one time, you have a high holding cost. If you order too little, you have make multiple orders and you have high ordering costs. So this is the optimal, and doing this, a total ordering plus holding cost combined is going to be 10,966, almost 11,000 for the year. Now, one tricky thing to remember is that you want to ignore the first element of the order quantities that it returns, because if you just print the order quantities, it adds this useless 0 at the front. These are 12 values for the 12 months, right? So month 1, 1600, month 2, month 3, month 4, month 5, month 6, month 7, month 8, month 9, 10, 11, and 12. So it returns you the 12 values, what to order each month, and it adds a 0. And that has to do with that Python indexes list from index 0, but the code wants to put the month 1 value in the first index. It's just easier to write code that way, so it just returns an extra 0. So the way you handle this is just ignore it. You just print out 1 colon means start from the first element of the list. So this is the 0th element. You ignore the 0th element, you start from the first element of the list, colon, and then you don't specify numbers, so it means go to the end of the list. So it gives you a sub list which starts from 1600 and goes to all the way to the end by doing 1 colon in square brackets, and that way you ignore the initial 0 that this code adds to the return value. Okay. And you can see that it adds, so you have, here you're calling Wagner algorithm with the quarterly demand, so 4 values, quarter 1, quarter 2, quarter 3, quarter 4, an additional 0 right here. So you can see it from the documentation that it's doing that. Okay. Now your task is to change the demand. So you want to change the November demand from 2500 to 1300, which is this number here. And you want to change the June demand from 1800 to 2200, which is this number here. Then you need to rerun the code and take a screenshot of the output and comment on whether the order quantity is changed or not. So that's your first task. That'll be your first screenshot that you'll need to submit for this lab. Continuing on, the next type of problem we're going to do is the news vendor problem. This problem exists when you can't have replenishment. So you have to decide at the beginning or the day before how much inventory you're going to carry, and then the next day or week or whatever the time period is, you sell from that inventory, and if you run low, you can't replenish. So think of it like a fashion apparel. You have or winter jackets, the classic example where news vendor is used. So you have a short selling period. Okay, you sell winter jackets in December, January, February, 3 months. If you're sourcing them from China or somewhere far away, the lead time might be 4 months or 5 months. So you order early, the jackets arrive in maybe October or November, you put them in the store shelves for December sales. And then let's say you run out of jackets in January. If you reorder now, they're going to arrive in June because the lead time is so long. So there's no point reordering. You can't reorder. Selling season is so short, so you just have to order all the quantity up front. Okay. So in this problem, if you order too much, you're going to have leftover stuff at the end that you have to throw out or sell at a cheaper value, at a salvage value. And if you order too little, then you miss out on sales, right? If demand is higher and you ran out, you're missing out on sales and missing out on profit. So either way, there's a cost, right? So here we do the ice cream example. You're going to go on an ice cream truck to sell ice cream. If you carry too little ice cream, you'll run out of ice cream quickly, and then you will not make all the sales you could have made. If you carry too much ice cream in the truck, by the end of the day, the leftover would have been melted, and you can't reuse it if it is melted and just throw it away, right? So that's the setup. Your forecast is you're going to sell 120 units of ice cream the next day. Ice cream costs you $2. If you don't sell it, a unit of ice cream costs you $2. If you don't sell it, it's just melted, you throw it out. If you do sell it, you sell it for $5, so you make $3 profit. If your demand is normally distributed with a standard deviation of 30, what is the optimal ordering quantity for you? Ordering quantity means how much ice cream you'll put in your truck for the next day. And what is the optimal ordering quantity if your demand has a Poisson distribution. So we have functions for both in stockpile.news vendor. The news vendor normal explicit function solves it for normal distribution, and Poisson explicit function solves it for a Poisson distribution. So you pass in, it has a parameter called revenue, which needs the sales price, which is $5 for us, right? So you can see I'm saying revenue equals sales price. Revenue is the parameter it expects in the documentation. So you can check the normal explicit function. It expects a revenue parameter. I just called my variable sales price because that makes more sense to me. So I have to say revenue, the parameter revenue equals sales price, my variable sales price. Purchase cost equals my variable called item cost. Salvage value equals my variable called salvage value. Demand mean equals 120. Demand standard deviation equals 30. Okay. And then for the Poisson, I call the news vendor Poisson explicit function. Poisson distribution does not have a standard deviation, so you just pass in the mean demand, everything else is the same, and then you print out the results it gives you. So if you expect your demand to be normally distributed, you're gonna put in your truck 127 or 128 units of ice cream, and you expect a profit of 302. Each ice cream gives you a profit of about 3, so you're selling about 100 units or 101 units of the ice cream and the rest is as like a safety stock, I guess, right? Because some days you will make profit more than 302 because demand will be higher. This is the average profit. So on an average you'll make 302, but some days you'll make more money. Some days you might make a little bit less, right? If your demand is Poisson, answer is pretty close in this case, because when the mean is high, far away from zero, Poisson is approximately close to normal. But in any case, if your demand was Poisson, you suspected it was Poisson, you would do this. Stock 122 units of ice cream. So your task is to change the mean demand to 10, standard deviation to 3, and then rerun this code by changing those parameters, and then take a screenshot to show me that you're able to do this computation with these different values. Mean demand 10, standard deviation 3. Okay, now we go to the reorder point problem, which is, you're going to order quantity Q at some reorder point R, which is called the RQ inventory policy, also called the continuous review inventory policy. And so let's solve a problem for that using this stockpile package. Assume that for an item, the holding cost is 20%. The item cost is $80. Stock out cost is 100. Mean demand is 250. Lead time for replenishment is 2 months. Ordering cost is 1200. So we do it for normal and Poisson distribution. Okay. So here, remember that it needs holding costs per time period. So it needs holding costs for each month. So first of all, you can't just pass it 20%. You have to go into a dollar value. So you multiply 20% by $80, the item cost, to get the holding cost in dollars per unit per year. But now, because we are running in the monthly time scale, because lead time is in months, we have to convert the holding cost to a per month basis. So we divide by 12 because there are 12 months in a year. So this is a little bit tricky with this package. It always expects holding cost in the time period that you specify the lead time in, or the time period that you specify your demand forecast in. This is monthly demand forecast, for example, right? So you sometimes have to divide your holding cost by 12, because usually we talk about annual holding cost. 20% is my annual holding cost. Okay, so then you just call this function. So it says RQ EOQ safety stock approximation. It has multiple approximations to find R, reorder point, and order quantity Q for the normal distribution. So the approximation I use with EOQ and safety stock, which is the approximation we study in our courses here in operations management course, supply chain management course, right? So that's why I'm using that one. And then it uses the Poisson distribution. It finds the exact values. So there's no approximation there. And then you can run this code to get the values. Now the Poisson one is going to take some time because it's a long algorithm. It tries many different values, I believe. It's an iterative algorithm. Okay, and then it shows you for the normal distribution, which is the case we study in our courses, this one. Reorder point is 688 and order quantity is 670. Okay. And after a while, after it's been running for 32 seconds, right here, executing 34 seconds, it takes about a minute or so to finish running, and then you'll get the output for the Poisson. Okay, now the SS policy is kind of similar to the RQ policy, except that instead of having you have a reorder point, which is small s, just like reorder point in RQ, but instead of always ordering Q units, you order up to S. So if your target level S is 800 and your small s is 200, and let's say you fell below small s, so you fell to 190, so 190 is below 200, now you'll order 610 because 610 plus 190 takes you back up to 800. So you order up to S, big S, when you go below small s. Very popular inventory policy used by a lot of companies, in their warehouses. They do an SS policy. Or this finally got done. So for Poisson demand, you want to have a reorder point of 499 and a reorder quantity of 685. Why is the reorder point lower for Poisson? Because Poisson is a tighter distribution. It tends to have less standard deviation than a normal. And so if you're really sure your product is Poisson distributed demand, because you have historical data to support that, you can use this as the reorder point. Otherwise, you should stick to the normal distribution. Okay. So for SS, again, we have the SS power approximation in the SS module for normal demand and SS discrete exact, where we call the use Poisson equals true argument to estimate it for Poisson. So again, we have the same problem we're solving here. The exact same parameters, just copy paste these lines down here. And then we call the SS power approximation, pass it all the mean demands and deviation of demand, holding costs, ordering costs, all of that nice stuff, and it'll give us that. Okay. Now, there is a problem though. This function has an error. I checked the code because I was getting values, a little bit dodgy, especially because it's not asking you for the lead time. Notice lead time of 2 months, you can't pass in the lead time. If you look at the documentation here to the SS module, here's the approximation. There's no parameter to pass in the lead time. And without the lead time, it cannot calculate sigma L properly, which is required in the formula. So if you try to pass in the lead time, it gives you an error. So this function has a problem. They made a mistake coding it. They did not use the lead time to fix some of the estimation of sigma L and mu L. So this S calculation here that they're doing in the code is wrong. I checked the code, it is incorrect. This is version 1 of Stockpile that I'm using. Okay, see, this is version 1, Stockpile 1.0 documentation. Okay, so you can't use this SS function here. And I didn't check the Poisson one, but it might have some problem as well. So I'm just showing you the code of how you run. Maybe they'll fix it in version 1.1, maybe they'll fix it in version 2. But for now, don't use this. That's why I'm not giving you a task to run this code again yourself. But I'm showing you the code when they do improve it. This is how you would call these functions, and you would pass this a lead time. When they do fix it, you'll have to pass it a lead time. You'll do comma, lead time equals, and pass in the lead time. Okay. Now, the last part, which is really awesome, is multi-echelon inventory optimization. Okay. This is really cool that it does that for you. And we do a heuristic calculation in the supply chain course. And this also does more advanced algorithm to optimize the multi-echelon inventory problem. So what is a multi-echelon inventory problem? Let's say you have a retailer where the holding cost of $3, lead time of 1 week to get replenishment from the warehouse. And the warehouse is always cheaper to hold inventory at the warehouse because, warehouses are outside of the cities. They're on cheaper land. They can store stuff more densely because everything is packed into pallets and not like put on shelves in like a retail store. So the warehouse has a holding cost of 1, much cheaper than the retail store. And the lead time from the warehouse to replenish the warehouse is 2 weeks because the supplier is far away. So warehouse needs to go back to the supplier and get inventory, new inventory. So it's 2 weeks. So how much inventory, what should be the inventory policy of the retailer and the warehouse? You can, if you just do like RQ or SS, RQ and SS does not assume for the retailer that you can get replenishment from the, that the warehouse can also get replenishment and has get out of stock too. RQ just assumes, okay, just for one facility, just the retailer, what is the inventory policy? It optimizes the individual facility. So inventory policy just for the retailer, inventory policy just for the warehouse. You can do it individually, but that individual optimization does not optimize the whole system. With echelon inventory, you can optimize the whole system and actually lower inventory levels because if the retailer runs out of stock, it can get it quickly from the warehouse. If the warehouse runs out of stock, it can get it from the supplier. So the warehouse needs to know how much inventory the retailer has, because if the retailer is carrying a lot of inventory, the warehouse doesn't need to carry a lot of inventory, right? Because it's very unlikely that the retailer will have stock, or if it's carrying a lot of inventory. Similarly, the retailer does not have to factor in the lead time of 3 weeks from the supplier, 2 weeks to get to the warehouse, which is in the middle somewhere, and then 1 week to get to the retailer. It only is factored in a shorter lead time, and so all these considerations make the multi-echelon inventory problem more complex. So the way we specify it is we're going to do the simple case of a serial supply chain, so retailer, warehouse, supplier, in a row, in a sequence. You could have like multiple warehouses, multiple suppliers, a more complex supply chain network, but those are more complicated how you specify them. But it does have some in the multi-echelon, in the GSM tree module, it has some functions to do more complex optimization, but I'm just showing you the SM serial module for simple. You have a retailer, which is replenished by one warehouse, and then maybe you can add a wholesaler, and then you can add a supplier, but it's one chain. At each level of the chain, just have one facility, right? So I'm just doing a 2-stage supply chain to keep things simple. Number of nodes is 2. A node order in the system, you specify the upstream node first, so the supplier or the warehouse first, which is node 2. These are just numbers to identify the nodes, and then node 1 is going to be your retailer. Now once you specify this, now you have to go in the order of the nodes. Because I called my retailer 1, the retailer's holding cost has to go first, and then because I specified my supplier or wholesaler or warehouse as 2, the holding cost of node 2 has to go second. Same for lead time. Lead time of node 1 goes first, lead time of node 2 goes second. In these multi-echelon inventory problems, each node has to have an ID. So think of this as a node ID. So the node ID of the warehouse is 2, the node ID of the retailer is 1. So you specify the order in the system that node 2 comes first, is more upstream, and then downstream is the retailer, okay, which is node 1. But then everything else is specified by the ID of the node. So node 1 stuff goes here, node 2 stuff goes here, node 1 lead time, node 2 lead time. The stock out cost, the demand, mean of the demand, standard deviation of the demand. Then you pass all of this data to this function called optimize base stock levels. It'll give you the optimal value of S. S star just means the optimal order up to level. It's the same S as the SS policy. That type of idea that you order up to that level. And then C star is the cost. So if you run this code, it's going to take a little bit of a while to run. And then it's going to show you, okay, so here's your base stock levels, or S star, the optimal order up to levels. You want to maintain a level of 148.46 at the warehouse and 113 at the retailer, and your expected total inventory holding and ordering cost is 388. Okay. Now, how does this system work? So the S star, the order up to level, whatever your lead time is, let's say your lead time is 1 week. Whenever at the start of a week, you say, okay, in this week I expect to sell 20 units. So you're going to place an order for 20 so that during the week your inventory level falls by 20 as you make sales. And then next week, the replenishment order price, you go back up by 20. So you're always trying to go back up to S. So whenever your lead time is, if you expect to sell a certain amount of product during the lead time, you place order for that. So as soon as your lead time is over, at that time period is over, and you've sold that amount of quantity, you get a replenishment, you go back up to level S. So it's just like small s and big S, you go back up to S. Here you're trying to go back up to S after every lead time cycle. So if your lead time is a month, after every month you try to go back up to big S or S star. If your lead time is 2 months, every 2 months you try to go back up to S. So that's how this is the inventory management is set up for multi-echelon inventory problems. Okay, your task is to change the lead time of the warehouse from 2, which is right here, to 1, and rerun the code, and then take a screenshot of your optimal stock levels. Okay, so this is how you can do a lot of inventory optimization calculations in Python using the stockpile package. And the purpose of this lab was to introduce the package, show you how to do various calculations that you may have heard about or learned the theory of in the different courses. I would say the most important ones is Wagner, the Wagner one, because that's just so common. Okay, so often in real life, you're ordering for forecasted demand. You have some demand forecast for the next quarter, next year. It goes up and down, there's seasonality, and you want to figure out how to do the ordering for that. So this is super useful that you can use. The other super useful is EOQ when you're ordering multiple products together. Oftentimes you have 3 or 4 supplies located in the same location, like same city. You can combine the shipments, shipment aggregation, and then you can use this EOQ to figure out, how much to order from each, and whether you want to skip certain products on certain ordering cycles or not, like I talked about. And then also really useful is the multi-echelon side. It's a little bit complicated to use. Like, if you start a serial, you have to learn the other functions and how do you arrange the parameters. Right, so, and news vendor one is really useful if you use Poisson demand. Poisson demand, also this RQ for Poisson demand is really useful. Reorder point problem for Poisson demand. Why? Because if you have products that don't sell consistently, they have lumpy demand. They are like your tail items. They sometimes sell a few pieces, then they don't sell for a while. For those items, if you assume normal distribution of demand, you will have overblown safety stocks. You'll have too much safety stock. Okay, as you saw here, Poisson gives you a smaller reorder point, so less safety stock. So if you take all of your C or D class items which don't sell a lot, and you set their inventory parameters, reorder points, using the Poisson formula, this Poisson function here, you'll reduce your safety stock in the system, you reduce your inventory cost without suffering any negative effects, because for items where there's lots of zeros in their demand, like they sell a little bit and they sell 0 for a few weeks and sell a little bit, for those items, Poisson is a better approximation distribution to use than the normal. And so this is also really useful. So with, and a lot of people who take supply chain courses, they can't do the Wagner Whiten algorithm. They don't know how to do multi-echelon stuff. They don't know how to do Poisson distribution stuff. So you learn how to do all of that using this code. So you are better placed than a lot of people who have taken supply chain courses. So I hope this was useful. You can follow this package, the documentation, or you can go to the GitHub page. You can just go, GitHub stockpile, right? And the GitHub page will tell you what the latest version is. So, when version 0.015, February 10th, which for somehow this release is called version 1.01. This is the version on PyPI, version 1.01. Anyway, you can always track the GitHub page for updates, and you can always, if it gets, when you do a pip install, it always gets the latest version of the package. And that is it for this lab.